Hello, welcome to a video on section 3.2, and we will begin on page 4 of the notes and go up to the middle of page 6. So in example 3, here we're asked to show that f of x equals x plus 2 squared of x squared plus 1 is not differentiable at x equals 0. So you want to show that the derivative does not exist at x equals 0 for this function. And after we do that, we do need to determine the reason for the non-differentiability, whether it's a discontinuity, corner, cusp, or vertical tangent, and we must support answer analytically. So what we'll do is we can generate the graph for this function by plugging into our calculator, or we can actually rewrite the function. To rewrite the function, it helps to take note that square root of x squared equals the absolute value of x. This is from the summer assignment, so hopefully you remember that. So f of x would just be this then. Now when we see absolute value, hopefully you could see that we can rewrite this function as a piecewise function. We also had this on our summer assignment. I believe those numbers 19 and 20. I know it was at the top of the second page of the summer assignment, where you had to take a function kind of like this, x plus 2 absolute value of x plus 1, and rewrite as a piecewise function, which actually could be written like this: x plus 2x plus 1 if x is greater than or equal to 0, because absolute value of x, remember, equals x if x is greater than or equal to 0, or negative x if x is less than 0. Also, we could rewrite it as x plus 2 times negative x plus 1 if x is less than 0. If I clean that up, f of x will be 3x plus 1 if x is greater than or equal to 0, or negative x plus 1 if x is less than 0. By the way, the equal sign for 0 doesn't matter. It could be for 3x plus 1 or negative x plus 1. And you'll see in a sec why it won't really matter. So if I graph 3x plus 1, if x is greater than or equal to 0, I'm going to have a y-intercept of 1 and a slope of 3. So it looks like this. And of course, negative x plus 1, y-intercept of 1, slope of negative 1 looks like that. So piecewise function. And you can see why it doesn't matter whether x equals 0 for 3x plus 1, negative x plus 1, because we see that they meet at the same place at 0, 1. So that would imply or make us suspected of continuity. Remember, for continuity, f of 0 must exist, which it does. We know it's 1. The limit as x approaches 0 must exist. In order to do that, we actually have to find the left and right-hand limits as x approaches 0, which is actually really easy. The limit as x approaches 0 from the left of f of x, we'll see is just from the right that I'm doing. So from the left, negative 0 plus 1, which is 1. From the right, 3 times 0 plus 1, which is also 1. And of course, f of 0 equals the limit as x approaches 0 for f of x. So we've proven that our function is continuous, yet that doesn't guarantee differentiability. But of course, our function has to be continuous to at least get differentiability, but doesn't guarantee it. Okay, so now how to prove if this is differentiable at x equals 1? Well, we do see a corner, which we talked about in the previous page of notes, so I think we pretty much know the answer to this question, or I think we pretty much have shown it in a way that we see a corner of the graph, but in order to show it, and also to prove analytically what type of, or what reason for our non-differentiability, the left-hand derivative hopefully you can see, is going to be -1, and the right-hand derivative is going to be 3. And that's because if I highlight, or maybe circle in red, it might be easier. That right there is responsible for the left side of 0, and that is a linear function with a slope of -1. That's why our left-hand derivative was -1. But in blue, we have the function 3x plus 1. That's a linear function. So that slope is 3. So we can say that the slope of the tangent on the right-hand derivative is going to be 3. So as a conclusion, f of x is not differentiable at x equals 0 due to LH deriv not equaling the right-hand deriv also we have a corner at x equals 0 since left-hand deriv and right-hand deriv exist. Basically, they're finite values. You know, they're -1 and 3, respectively, but don't equal each other. So that's the story with example 3. That's what we show is not differentiable. It helped to rewrite the function at square of x squared is absolute of x, but then write as a piecewise function, graph it, and then we can look at each portion of the piecewise function. Say, okay, we have 2x plus 1, -x plus 1. Those are linear functions. We could get the slopes of those to get the derivatives. Of course, prove that it's continuous first, which we did. And then we can deduce that fx is not differentiable at x equals 0 since the left and right-hand derivatives don't equal each other. And we have a corner because they're finite values that don't equal each other. Now remember, for a cusp or vertical tangent, you would need your limits to hold infinite values. And of course, if you have discontinuity, you just stop right there and say, oh, it's discontinuous. Of course, it's not differentiable. Because remember, discontinuity leads to differentiability, just how differentiability leads to continuity from the statements we made in pages 1 and 2 of the notes. Other things to take note is that most functions are differentiable where they are defined. Polynomial functions, which are continuous, they'll be differentiable actually everywhere because polynomial functions have domains of all real numbers. Rational functions, which don't have domains of all real numbers, but where they are defined, they are going to be differentiable. Likewise, the trig exponential log functions. And we also will go into sums, products, quotients, integer powers, composites, all that fun stuff. We'll see later. So now we're going to do a little bit of calculator work. Now, I'm hoping that this video will be somewhat easy to follow from here on out because I was hoping to download something called the TI-84 emulator where you can actually see the calculator on the screen. But unfortunately, I can't get it to download correctly. So I'm going to try to walk you through it and hopefully that'll make sense. So what we're going to do is we're going to try to calculate the numerical derivative of a function at a given point. So here we have f of x equals x cubed x equals 5. This is example 1 from the section 3.1 notes. And you might remember that when we found f prime x, it was actually 3x squared. And of course, we're asked to find f prime of 5. Now that's pretty easy. We should know what to expect. We should expect 75. Plugging 5 in for x, 5 squared is 25, 3 times 5 is 75. And again, how we found the derivative 3x squared, that was straight from the notes, just using the formal definition of a derivative or that limit definition as x approaches h, or sorry, as h approaches 0 of f of a plus h minus f of a all over h. But I'm not going to go through that because that's in the notes. Here what we're going to do is we're going to see what the calculator says. So there's a couple ways you could do it. If you hit the math button in your calculator and select option 8, you'll see something that's called n-deriv. And when you do that, math, option 8, n-deriv, Now you might see something that kind of looks like this in your calculator. And don't let that freak you out. It's actually a good thing if you're seeing that. So if you're under the math print mode, which is the new operating system for these calculators, it's going to look more like this right here. Another way to access this too is if you hit Alpha, Window, Option 3. You'll see the same thing. It'll say NDeriv. Now, if you're in the old operating system, you're going to have to do it like this. We're going to have to type in the function first. That's always going to be the original function. Then you have to state what your with what respect you're taking the derivative too. So with respect to x, that will make more sense when we get to later in this chapter, with like taking the respect to x. But you do have to let the calculator know that you're taking the derivative with respect to x. And then, of course, this is what we're going to evaluate at x equals 5. So you can type in that way if you're under the old operating system. If you're under the new operating system, really easy. You put in x here. That takes care of the respect part, respect to x. This is going to be our function. We're going to put x cubed. And this right here is going to be x again. And that's going to be 5. This is how we evaluate. Evaluate at x equals 5. So if you punch this in the calculator, I'll rewrite it again. You should have d dx parentheses x cubed, the bar, x equals 5. The calculator should give you something like this. 75.001, which we can approximately say is like 75. So we can say that with confidence that, okay, we know that the derivative of x cubed at x equals 5 will be 75. Now it's a little weird that it doesn't give 75 straight because 75.00001. I may have said too many O's, sorry about that. So let's try to understand what the calculator is doing. So how does the calculator do this? So when it calculates NDeriv, which is short for numerical derivative, it does it in the following manner. It actually does something called the symmetric difference quotient, which is right here. And it's pretty simple. So we have y equals x cubed, right? And we want to evaluate the derivative of x equals 5. So say a equals 5. And say that you add a 0.001 to 5. So let's say I put a 5 here. I add 0.001 to 5, and I subtract 0.001 from 5. And divide that by 0.0002. If you work that out, that's what the calculator is doing. So this is what the calculator does. It actually will do that when you ask it to give the derivative of a function at a certain x value. It's pretty similar to this, which we saw when we did the formal definition of a derivative. Remember, we would do the limit is h approaches 0 of f of a plus h minus f of a all over h. But the difference here is that it's an approximation. Both of these are. They're not limits. So when we do the derivative, we do as a limit as h approaches 0 to get the precise value. The calculator will do an approximation instead, which is pretty close to the actual derivative. If you look back at the difference quotient again, Notice how they have a point to the right of the point where we want to find the derivative, or the slope of the tangent line, right? And they have a point to the left as well. And again, that's a plus 0.001 for x, a minus 0.001 for the left point for x. If you connect the 2 points that are close to point P, what you'll notice is that you're drawing a secant line. But we're hoping that secant line is close enough to the tangent line, which is what the calculator does. Of course, when we go through the actual derivative analytically, we're finding the slope of the tangent line. So we'll do an example 5 is we'll actually find a difference quotient, symmetric difference quotient for this function, and then we'll use a calculator to graph x cubed, and then we'll look at some other examples after that. But for now, let me stop the videos just so the video is not too long. And also, just to be honest, I do have to start getting ready for the parent-teacher conferences. So I will continue this video in a little bit, and we will go through examples 5 and 6, as well as 7, and then, of course, 8. And we'll stop the video at differentiability and local linearity.